All right. So we'll start with the last structure which we are going to study in this particular subject. So this is the design of Intz tank, and this particular tank is very important. And basically, this is a storage structure. So water is whenever we have water treatment process. So the water is pumped from the intake well, for which jack well and pump house is used. So we have already seen the design of that. Then the water is transferred to the water treatment plant, where this all the process like filtration, screening, aeration, coagulation, flash mixer, clariflocculator, everything is done. Okay. And further what happens is the water, the treated water is transferred for the distribution process. And in the distribution system, what happens, the water is first of all stored in the elevated service reservoir. So mostly it is in water tank, and then it is transferred to the through the pipe system to the houses. Okay. So as far as this Intz water tank is concerned, so you can see on the left hand side, this is a constructed structure of Intz water tank. This is a photograph, and on the right hand side you can see there are different components which we have to design as a structural engineer. Different components are there, like we have to design the top dome, then the top ring beam, then the side wall, or we can also call this as a container wall. Then we have a bottom ring beam, then we have a conical dome, and the lastly that is the bottom dome. So all these components combinedly, they are the part of the container. So container means the water is contained in this particular structure. Okay. The rest of the portion is basically a support system, which consists of the bottom ring girder. There are columns, there are braces, and there is a foundation. Okay. So all these components, there are roughly 15 components to design as far as this Intz tank is concerned. Okay. So I'll be sharing the PPT after the topic is over. So please note down this correctly. Okay. So I'm not giving you time to note down this figure. So this will be available in the Google Classroom. So no need to write down. Okay. So now let us start first of all with the design of containers. So usually the container shape is like this. We have a dome at the top which is covering the container. Then this dome is supported by the top ring beam, and then we have a cylindrical wall which is generally supported by the bottom ring beam, and then there is a conical dome, and then there is a bottom dome which is basically resting the which is supporting the water. So all these dimensions we have to find out such a way that the capacity or the required capacity of the container should be maintained. Okay. So generally what happens, if we consider the diameter of the container as capital D, which is somewhere over here. Okay. So in reference to this D, all the dimensions they are considered. Okay. So usually the height of the wall is usually taken in the range of zero point 0.6 to zero point 0.7 times D. Okay. Then the rise of the dome, that is the top dome, it is considered in the range of 0 D by 5 to D by 6. Okay. And usually the bottom dome has got a rise of say zero point 0.2 D, and the diameter of this bottom dome is usually 0.6 D. Okay. So these dimensions mostly they are given. If they are not given, you have to identify using this standard formulas. Okay. Usually this angle is basically 45-degree. Okay. So this conical dome usually it is kept at an angle of 45 degrees so that the forces can be distributed properly, right? And usually what happens is, like whenever we have a container, so the container should not be like this. Okay. That means इसका जो aspect ratio है, that should be maintained, and container should be looking like this. Okay. So it has got a wider diameter and thus lesser height. Okay. So with this, let us start designing the Intz water tank. So now for the design purpose, the capacity of the Intz water tank is given to you. So basically we have to design the Intz water tank for a capacity of 1000 meter cube. So it should hold a water which is having a volume of 1000 meter cube. As far as the support system is there, so 8 columns we have to provide to support this entire container. And this entire container is supposed to be elevated, because if the height is more, then the pressure will be more, isn't it? So this height is given to you. So we have to keep this container 16 meters above the ground level. So this is the height of the staging which is given to you. And the depth of the foundation below the ground level, it is usually given, it totally depends on the soil type. So here 1 meter depth is given to you. And at 1 meter depth, the SBC of the soil is obtained. And we can see that the SBC is, let us say, 250 mm. And as far as grades are concerned, so we are using the least possible grade, that is M25 and Fe415 grade steel. So this is the basic information based on which now we have to design the foundation part. Okay. Oh, sorry, not foundation, Intz tank. So let us continue this. So with this, we have to first of all find out the design constants. So for M25 grade concrete, we have to find out the value of SBC, and the value of SBC from the IS code, that is 8.5, and Fe415, the sigma ST value is 130. Okay, so can anybody give me the values? So modular ratio, I think I have already calculated the values. So modular ratio is for Fe415 and N25 grade concrete is 10.98, and the K value, okay, that is 0.418, the J value is 0.86, and Q value is 1.527, I suppose. Barabar hai? So these are the design constants which we have been used till now, and in this problem also we'll be using. Okay. I hope this is clear to everybody. Are there any questions? Yes, students, are there any queries? Shall I continue?
Yes, sir.
Okay, fine. So now the very first step is to find out the dimensions of the tank. And like I said earlier, everything is depending on the D. D is nothing but the inner diameter of the container, that is tank container. So what we are doing is we are assuming the height of the tank, okay, height of the tank as 0.75 times D. So if you calculate specifically the volume of this particular tank, so it can be pi by 4 d square into height of the tank. Okay, so this is basically a volume formula. So right now the volume is given to us. So we need to have a volume of water of, let us say, 100 meter cube. So from this we can just substitute the value. So pi by 4 d square, and h is nothing but 0.75 times d. Okay, so with this, can you give me the value of d? How much is the value of d? Somebody please tell me. कितना आ रहा है?
तो 11.92.
यस कृणाल, कितना है?
तो 11.92.
11.92. Is it so?
Yes, sir.
Okay, so since this is 11.92, so we can round it off to the higher side, and we can assume the diameter of the container, that is the diameter of the cylindrical wall, as 12 meter. So if we finalize the diameter value as 12 meter, so accordingly the height of water tank will also change. So height of the water tank is nothing but 0.75 times d, which we have assumed over here. So accordingly the height value comes out to be 9 meter. Okay, now with the help of this, now we have to find out the other dimensions. Let us say we have a conical dome. Okay, so the conical dome, usually its height is called as h0, and this bottommost conical dome, we take this as 0.2 times d. Okay, so if you refer this figure, I am talking about this bottommost conical dome. So this height is nothing but 0.2 times d. Okay, so if you take the value of d as 12 meter, so your h0 value, that is the height of the bottommost conical dome, it comes out to be 2.4 meter. Okay, then we have to assume the diameter of the supporting tower, that is d0. So when I say d0, d0 is nothing but this one. Okay, this one. Okay, this is nothing but your d0, and this is nothing but your h0. So we can assume this as 0.6 times d, or we can simply take this value, that is since this is a 45-degree angle, so That way also we can do it. But anyway, so we can assume this value as d minus 2 times h0. Okay, so why I'm taking h0? This is I think I have made some mistake. Let me go back. H0 is a different term. uh, yeah, this is h0. Sorry. Okay, कहाँ गया? Yeah, this h0 is nothing but the height of the conical dome. That is this height. Okay, not this height. Okay, this is not h0. This is h0. Okay, so what will happen? Generally, this is a 45-degree angle. So this distance will be also h0. So this distance will be also h0. So this diameter. Okay, so this diameter is nothing but this d minus h0 minus h0. Okay, so here we can have the value of d. So value of d is basically 12 meters minus 2 times h0. H0 is nothing but 2.4. So this is going to give us the value of d0 as 7.2. Is it clear to everybody? Yes, students, is it clear to everybody?
Yes, sir.
Okay. Okay. In this picture now everything will be clear, okay, because here all the notations are given. So uh, here we have assumed the value of h. Okay, so this h we have already calculated over here, and this h is nothing but 9 meters. Okay, so this was a rough idea. Okay, so this was a roughly we have calculated, and based on that we have assumed all the dimensions. So we are assuming the bracings. So yeah, this for the timing you forget about this. Okay, now we are going for the other dimension, that is h1. H1 is nothing but the rise of the top dome. So when I say rise of the top dome, so this is nothing but h1 value. So here what will be the rise? So that value is there. So generally we take this as d by 6, where d is 12. So 12 by 6, so this will be your 2 meter. Okay, then we have the rise of the bottom dome, that is this one. Okay, ye wala. Okay, so this rise is nothing but 0.2 times d0. So d0 is 12, so this value becomes 1.44 meter. Remember, this is your h0, this is your h2, and this is your h1. Okay, now since there are two domes, one is the top dome, okay, and this is your bottom dome. So we have to find out what are the radius of these top domes and bottom dome. So to calculate the radius of this top dome and bottom dome, we have to use this expression, that is h into 2 times r1 minus h equals to d by 2 whole square. Okay, so when I talk about the radius of the top dome, so I'm calling this as r1. So this is nothing but the radius of the top dome. So this is h1 value. So h1 value is nothing but the height of the top dome, which is 2 meters. The r1 value is unknown. Okay, the h1 value is nothing but the height of the top dome. So this is nothing but your 2 meters, and the diameter of the top dome is 12 meter. Okay, so if you solve this, okay, you are going to get the r1 value as 10 meters as shown over here. Okay, now if you want to calculate the radius of the bottom dome, so this will be h2. So h2 is nothing but the height of the bottom dome, so it is 1.44. So radius, this will be unknown. The height of the bottom dome is 1.44 one more time, and this diameter is nothing but the 7.2. So this is the 7.2 diameter. Okay, so how this 7.2 came? It is nothing but 12 minus 2.5 minus 2.4 minus 2.4. So again, if you solve this, you are going to get the RT value as 5.22 meters. Okay, so in this way, now all the dimensions are now known to you. Okay, we have earlier assumed this value h as 9 meters. Okay, but now it was calculated using only this much portion of the container. तो यहाँ पर जितना पानी रहेगा, that was 1000, but actually there will be a water in this region also. Okay, so now we have to calculate the actual capacity, and accordingly we have to reduce the height of this particular Intz tank. Okay, so now for this purpose, what we will do, we will try to find out the area of this entire portion, that is from here to here, here, then here, then here, and then here. So whatever water is enclosed in this particular portion, that we have to now calculate, and it should match with the required volume of 1000 meter cube. Okay, so now for this purpose we have to do some calculation. So here you can see the tank capacity. So this tank capacity is nothing but your 1000. So this is the first, it is nothing but the volume of the cylindrical portion. So when I say cylindrical portion, I'm talking about this one. Okay, so what will be the volume of this cylindrical portion? It is nothing but pi by 4 d square into h. So where this h I am keeping this as unknown. Okay, because I have to adjust the height. The diameter is already known to me, so diameter is nothing but your 12 meter. Okay, so this is the first portion. Okay, so this volume I have to calculate, then plus the volume of the conical portion. So when I say conical portion, so this is the conical portion from here to here. Okay, so this conical portion volume can be calculated by simple expression pi h0. H0 is nothing but this height, that is 2.4 meter. Okay, d, that is the larger diameter, that is 12 meter. D0 is nothing but this one, that is 7.2 meters, and again this will be 12 and this will be 7.2. So now in this case this is going to give you the volume of this complete portion. What you will find that this portion is already added, so we have to deduct this portion, that is the volume which is there below the bottommost dome. So this bottom dome volume now we have to deduct. So this can be calculated by simple expression pi h square. So h is nothing but the height, and height is nothing but 1.44. This r2 value, that is the radius of the bottom dome, it is 5.22, and h2 value is 1.44. Okay, so now everything is known except this h. Okay, so give me the value of h, someone please do the calculations part. Yes, anybody give me the value of h? बताओ भाई.
So 7.54.
7.54. Someone please cross check. Yes, someone please cross check this value. Is it okay?
Yes, sir.
Okay, good. So we'll continue. So we have calculated this h value, and if we keep this h value at 7.54, then the entire container will be having a volume of 1000 meter cube. Okay, so now let us keep this particular value as 8. Okay, because in actual practice you cannot have the exact height of 7.54, so this will be 8, it is rounded off to higher side. So this is going to create some additional volume. Okay, so we have been asked to design the Intz tank container for 1000 meter cube, so this will be slightly more than that. Okay, that's not an issue. Bigger is always better. So let us quickly start with the final designs now. So let us start with the roof dome now. So as far as roof dome is concerned, we have already designed the roof dome when we have studied this pump house, isn't it? In the pump house we have designed the dome, so the same procedure is applicable over here. So now as far as this roof dome is concerned, we have h1, this is the rise of the roof dome. Okay, and this is the diameter, that is d. Okay, so your d is nothing but your 12 meters. Okay, and the radius, so this is the center. So from the center, the radius is now 10 meters. So if you take this angle, the angle between the vertical axis and where this dome is ending, so this angle comes out to be 36.87. So this is nothing but tan inverse of, this will be the opposite side is 12 divided by 2 divided by the hypotenuse. So hypotenuse is nothing but r1, that is 10. So this is not tan inverse, this will be sine inverse, sorry. Okay, so this comes out to be 36.87. Okay, you can also calculate the same using tan inverse also. So now with this, let us quickly start with the design. So first thing is, we are assuming the thickness of this top dome as 100 mm. Okay, and accordingly now we have to go for the loadings. So the load calculation, the very first thing is the dead load. So dead load is nothing but thickness into the density of the dome. So the thickness, we have already assumed this as 0.1. The density of the concrete is nothing but 25. So this is going to give us a load of 2.5 kilonewton per meter square. Okay, now as far as live load is concerned, this is elevated service reservoir, and no one is going to climb on the top dome. Okay, some persons may climb just for the maintenance purpose. That's why the loading which we are considering in this case, it is 1 kilonewton per meter square only. Okay, because this is a roof and it is not very frequently accessed. But exactly reverse of this was we have seen in the design of GSR, and for that purpose we have used the greater amount of live load, if you remember correctly. Okay, so now if we combine all these loadings, so your total load, that is the total load UDL which is coming on the top dome, it is something like 3 kilonewton per meter square. Okay, so now as you know that this top dome will be subjected to the meridional stresses as well as the circumferential stresses due to the vertical load. So your load will be like this, isn't it? So because of this, there will be a circumferential stresses like this as well as the meridional stresses. Okay, so let us call first of all calculate the meridional thrust. And if you remember, we have calculated the meridional thrust with the expression that is W into R divided by 1 plus cos of theta, where W is nothing but the UDL, which we have already calculated this as 3. The radius is nothing but 10. Okay, so here the r1 value we have already calculated as 10, and the theta value, so theta is nothing but this angle. Okay, so theta value we have already calculated 36.87. Okay, so can anybody give me the value of meridional thrust?
19.44.
Sorry,
19.44.
19.44, this is kilonewton. Okay, now we have to calculate the stress. So this is the same value. So this is 19.44 into 10 raised to power 3. As far as area is concerned, we have considered the thickness as 100 mm and other side will be unity. Okay, so I think this is coming out to be 0.1944 newtons per millimeter square. So as you can see, it is very much less than the permissible stress in concrete under direct compression. This is for M25 grade concrete, the value is 8.5. So you can see, as far as these stresses are concerned, they are well within the permissible limit. So you don't have to worry about this. Okay. So now let us quickly see the circumferential stresses also. So if you remember, circumferential stress we have calculated using this expression, where now W is basically 3, that is I think it is 3 or 3.5. तो यहाँ पर भी तुम्हारा 3.5 आएगा. Okay, so this value will slightly increase, but definitely it will be within the permissible limit. So this is 3.5, the radius is 10, and theta, so theta is nothing but 36.87. Okay, please tell me the value of circumferential force.
8.55.
Sorry, 8.5.
Yes, sir.
Okay, this is kilonewton. Okay, so we have to divide this by area. So this is 8.5 into 10 to the power 3, and area is 100 into 1000. So this will be something like 0.085. Is it so, or 0.85?
Correct.
Correct hai? So here also you can see the circumferential stress which is caused due to the circumferential force. This should be in tension. Okay, so here you can see the tension is there in this particular region. Okay, so this should be less than sigma ct permissible. So for M25 grade concrete, the value of permissible stress in concrete in direct tension, it is 1.3, and you can see it is still safe as far as the tension is concerned. Okay, I hope this is clear to everybody. So the steel. So steel is basically we are providing the AST minimum, that is 0.24% of the cross section area. So this is cross section area is 100 into 1000. So this comes out to be 240 square. ठीक है. So 8 dia bar at the rate. कितना आएगा इसका स्पेसिंग बताओ.
209.
200.
209.
But will be providing 100 center to center because the thickness over here, this is only 100 okay, otherwise there will be a punching action, right? So that's why we have to provide 100 center to center, right? So I hope this portion is clear to everybody. Are there any queries? Yes, students, are there any queries? Shall I proceed? Yes,
Yes,
students,
sir.
shall I proceed?
Yes, sir.
ठीक है. So we will take one more design. So this is the design of top ring beam. So this also we have done in the previous, that is the design of top ring beam in the pump house. Okay. So you can see the meridional thrust was there. Okay. So this was a meridional thrust. We have already calculated the value. The meridional thrust was something like 19.44. This was the value. Okay. So let me write down. So this P value is something like 19.44 kilo Newton. So now this we have to calculate its horizontal component, that is the circumferential force. So we just have to take the sine, we have to take the cos of this particular angle, and the theta is 36.87. So this is 36.87 degrees. Okay. So all we have to do is just substitute this value. So this is 19.44 and theta is 36.87. Okay. How much is this? कितना आ रहा है?
Sir, 15.55.
Sorry,
15.55.
15 or 50?
15.
15.55 kilonewton. Okay. So now this is the circumferential force, and this circumferential force is going to create a hook tension. So hook tension is nothing but circumferential force into d by 2. So this is 15.55. Your diameter is 12 meter. So 15.55 into 12 divided by 2. How much is this?
93.3.
93.3. So this is a very large value. So this is an axial tension which is there in the beam. So to resist this tension, we have to provide the significant amount of steel so that the cracking can be restricted. So AST is nothing but hook tension divided by sigma ST. So this is 93.3 into 10 raised to power 3. Sigma ST, we are taking this as 130. So how much is this AST?
717.7.
717.7 millimeter square. Okay. So now since this is a beam, we have to provide minimum 4 number of bars. Okay. 4 से नीचे हम लोग बार प्रोवाइड नहीं कर सकते हैं. Okay. So can you tell me how many bars are required if I provide 12 dia? कितने बार्स लगेंगे? यस, 12 के कितने बार लगेंगे?
सर 6.34 and 8.
सॉरी,
8 लगेंगे सर.
8 बार लगेंगे, ठीक है. सो दिस इज 8 numbers. Okay, so what we can do is we can provide one over here, one over here, one over here, one over here, and in between also we can provide, because these bars are provided to resist the tension. Okay, and we can assume the size of the beam, that is 300 by 300. You can even assume less also, because anyway only tension is developed in this particular beam. So if we assume the dimensions of the beam as 300 by 300, let us calculate the permissible stress or the actual stress in the concrete beam. So the maximum hook tension, it is something like 93.3 into 10 to the power 3. So area of the concrete is basically 300 by 300. M value, I think it is 10.98, and AST is nothing but pi by 4 into 12 square into number of bars, that is 8. How much is this tensile stress in concrete?
0.93.
Sorry,
0.93.
93 newtons per mm square. And as you can see, this is less than the permissible limit, that is 1.3, that is the permissible stress in concrete in direct tension. Okay, so this is how the design is done. And this we have to provide the, this is the stirrups. Okay, so we can provide nominal stirrups. Okay, so you can refer IS 456 and whatever nominal stirrups are there, that you have to provide, because this is not a simple beam which is subjected to bending. This is a beam which is subjected to axial tension. Okay, so we will stop over here, because in the next class I have to cover the cylindrical wall. It's a long thoda sa lengthy topic hai, so we will cover in the coming classes. Okay, so as far as this part is concerned, is everything clear to everybody? Are there any queries? Yes, students, are there any queries?